AP Stats, we are in the next handout for, or the next few handouts for the second half of Unit 10 over chi-square inference procedures. There's really only two more major topics left. I think I'm going to add a third one in there just to as a review for everything that we've gone over pretty much, or maybe just to help practice identifying the exact type of test that you're going to want to use. There are three different types of chi-square tests that we're going to be tested over, or that the AP exam could possibly assess you over. So practicing knowing which type of chi-square testing situation is the case and which test is most appropriate for a particular set of data, that's a skill you need to practice. So there'll be, for the most part, 3 videos, I think. That's what I'm planning on, 3 total videos, and the third one's going to be some sort of a practice worksheet of some sort. There's only going to be, again, one homework assignment for this half, the second half of the unit. So we'll go straight into it. So the 2 types of tests that are left over are for specifically situations where we have contingency table data or two-way table data. So some way, somehow, we have 2-dimensional data. And we have 2 different types of tests, and the first one is homogeneity, the second one is for independence between variables. And there's some subtle differences between the 2, and it's kind of easy to confuse the 2, which is why we need that extra practice after the second of the 2 handouts that we're going to be needing for this second half of the unit. So that's why we need a third one. So homogeneity. This is a test to see if populations are like each other with respect to a categorical variable. So if you compare 2 or more populations with each other regarding what they look like with respect to a particular categorical variable, do they look the same? Do they not look the same? If they look the same, then we call them homogeneous. So specifically, they would be called homogeneous if they have the exact same distributions for that one particular variable. The category proportions are the same all the way throughout for both populations, or for all populations, because there might be more than 2. So we'll go straight into number 1. Number 1 starts with a question. Has modern technology changed the distribution of birthdays? So distribution of birthdays is going to be compared for 2 different time periods. It continues with more babies being delivered by planned C-section. Mrs. Smith's statistics class hypothesized that the day of the week distribution for births would be different for people born after 1993 compared to people born before 1980. So the idea is before this technology, C-section was available or very, very common. The delivery happened when it was going to happen. So there was no planning a delivery. The baby comes when the baby comes. So, however, if you have this sort of technology, you get to plan the procedure ahead of time. If everything goes to plan, then you can have the birth happen on a specific day. So you can plan when those days happen. So maybe there's something external there that would influence the day of the week. Then it continues. After all, why would a doctor plan a C-section for the weekend? So that's one thing you can consider. Maybe doctors would not want to plan it on days that are inconvenient for them, so they'd rather plan it on days that are convenient for them. So we'll continue to investigate. They selected a random sample of people from each of both age categories and recorded the day of the week on which they were born. The results are shown in the table below. Is there convincing evidence that the distribution of birthdays has changed? So here we have 2 samples. This is going to be the key distinction between a situation where we would use a test for homogeneity and a situation where we would use a test for independence, which is the next handout. The key distinction being that we have 2 or more populations that we're getting samples from. So you have multiple samples. So that's the big difference, multiple samples. And I'll repeat that later for that practice worksheet that we're going to have afterwards. So we have 2 samples. Sample 1, with its sample size N1, let's say, 77. Sample 2, with its size N2, 73. Now we're going to go ahead and add those 2 and combine them on a contingency table. Those add up to 150. So we consider the total, or the big total, whatever you want to call it, the total, because I'm going to make a distinction between the actual total, the combined samples, from each sample total. And then we're also going to think of each category total. So letter A, state the null and alternative hypotheses that Mrs. Smith's class should use to test for a difference in the distribution of birthdays for these 2 age groups. So we'll start off with the null and alternative hypothesis. So the null hypothesis first. We're going to want to state that qualitatively first, because we might not understand how can I test for a difference between the distribution across these two different populations. So we'll just go ahead and state that they should be the same with respect to that variable categorically. So we'll start off with the distribution distribution. I'm misspelling that word. Distribution of, that's a particular variable, day of the week. I'll continue. One was born. Is the same for both age groups. And there's two age groups. The before 1980 and after 1993. The null hypothesis, they're not the same. So it's going to be literally everything that I just wrote, but I'm going to insert the word not somewhere. So before the word same. So is not, or before the word the, is not the same. And we'll leave it at that. So I'm going to rely on the mathematics, the work that I'm going to show in just a bit, to clarify what we mean by the null hypothesis. So for that, calculate conditional relative frequencies that can be used to compare. So they're gonna tell us how we would compare these two distributions. So calculate conditional relative frequencies that can be used to compare the distributions of birthdays for both samples. Then calculate expected counts for the two age groups, assuming that there is no difference in the distribution of birthdays. So how do we calculate the expected counts that they want us to do? So that's going to be a little tough at first, and the reason why it's going to be tough, mathematically speaking, it's because we have different sample sizes. If I look at those sample sizes, one of them is 77, the other one's 73. So they're different. And most of the times that's going to be the case where these sample sizes are different. If it's a test for association like we're looking at tomorrow, those category sizes are going to be very different for sure. So we're going to have to come up with a foolproof way to come up with these expected counts, regardless of that situation. So that generalizes for any sample size for either category or either group. So how do we get this done? What we do is we use the fact that we have 77 in one age group, 73 in the other age group. We take those as percentages out of the total for that age, or total for these combined populations. So we have a total of 150 people, and we need to keep in mind that 77 out of those 150 were in the before 1980 category. 73 of those same 150 people were before the after the 1993 category. So they're in the after 93 category. And what we do in this situation is we're going to go ahead and assume, so expected counts are going to be calculated under the assumption that we should have a proportional distribution of people born on Sunday for either category. So we have a 12 and a 9. So what should those 12 and that 9 be for either of those cases? So we had 77 out of the 150 that were in the before 1980 category. Well, we should have that same proportion of people born on Sunday out of the 21. So it should be uniform for each day of the week. So that 77 over 150 proportion is what we're going to use to calculate either of these two expected counts. And the way we do that, for the first one, so for that first one, that's Sunday. And if you remember, the symbol that we used for and was the intersection symbol. So Sunday and, let's say, before 1980. Then the way that we do that, this is going to equal to, well, those born on a Sunday and before 1980 should be, well, first off, there were 77 out of 150. This is the percentage or proportion of all those born before 1980 in the sample. And that's going to get multiplied by the 21 who were born on Sunday total. So it should be that same proportion out of the 21. which I'll use a calculator to figure that out. 77 over 150 times the 21, and I'm getting 1078. That one I didn't need to round. So 1078. So what should that 9 have been? So we do a similar calculation for that one. It's going to be, in this case, there's a total of 73 people in the after 1993 category. So 73 out of the 150 is the proportion that we would like it to be. And then that's going to get multiplied by the 21 to scale it. That should have been 10 over 22. And that calculation is going to be mimicked all the way across each of the 7 days of the week. So basically what that should be is, well, 77 out of 150 first off. 77 out of 150 is 51.33% of all those in the sample. So the 77 that were born in 1980, or born before 1980, sorry, that makes up 51.33% of the sample. So the 73 out of the 150, what percentage is that? That's about 48.67% out of the 150 that were born after 1993. So those percentages should be the same all the way throughout if there is no difference in the distribution of the day on which these people were born for either age category. So that's the way that we're going to do this. So then there's a mathematical shortcut for this. The way to get that, if you're stuck inside one particular cell, so let's say you're in this cell, Monday before 1980. You'll be looking at the total for that corresponding dimension. In this case, that's a column total. Then you look at the row total for that same cell. So the row total is going to get multiplied in there eventually. And that's going to get divided by the 150. So the formula for an expected count. Expected count is equal to the row total. That's going to get multiplied by, and it's no particular order needed, column total. And this will get divided by the actual total. So I could write the total if you want, big total if you want. And that's our formula for finding the expected counts. So really what we were doing, in this case it was the column total divided by the total, and that was giving us the percentage of the people in that column out of the entire combined sample, and I think I erased too much, which I'll write those back in there a little bit. And then you're multiplying that by the other category in the other dimension. And that's how you would get this done. But because multiplication and division, there's a commutativity that we can employ, so it doesn't matter what order we multiply and divide, as long as everything is in the correct place. So we can have it like this as one rational expression, row total times column total divided by the big total. And what I'll do is probably edit out where I calculate all of those expected counts. So what I'll do is I'll go ahead and calculate all of these by hand one by one, and then we'll come back when I have them all ready. And here they are. So here's all our expected counts. And expected counts aren't done for the column totals or the row totals at all, or the total. So it's everything else that's not a total. How many entries do we have, by the way? So there are 7 days of the week, and then there are 2 populations, one before 1980, one after 1993, 14 entries. Now the word entry is something that you would, it's a computer science term, and it's also a mathematical term. Computer science, when we're thinking about arrays and what we enter for every member of an array. And arrays mathematically are matrices. So the word entry comes from the mathematical discipline of matrix algebra. So we want to think of these as matrices. This is a 7 by 2 matrix, because later on when we use the calculator to do some of this stuff for us, we're going to want to store variables as matrices to plug into the statistical test application or function. And I think we'll see that before the end of this one particular problem. So we have all the conditional relative frequencies. Those are all the expected counts. So I'm going to go ahead and say see the table above, because I wrote it up on the table. So those are my expected counts. Letter C. Use an appropriate statistic to measure the difference in the two distributions. This is going to be done very similarly to the one that we had done before, or the way that we had done it before. We're going to be using a chi-square statistic. Now, we don't call it a chi-square statistic. We're going to call it the homogeneity statistic for now, because it's not exactly chi-square. For most statistics in this course, in the practical sense, or in the practical cases, we don't have exactly chi-square distributions. We have approximately chi-square distributions, finite populations and things like that. But as the sample sizes get really, really big, it's okay to use a chi-square distribution anyway. So we'll start with the letter H. This is going to tend towards a chi-square, which I won't write that. But it's going to equal to the same idea. There's going to be a sum of expected counts and observed counts being compared. So it's observed minus expected squared, all divided by the expected value. And this is going to be done over 2 dimensions. So normally in mathematics, if I wanted to do this for a two-way table, or data that's given on a two-way table, you're going to have 2 different summations. There are 2 entries, or 2 dimensions per entry. So we have an observed entry. We can call that I and J minus expected, what the entry was expected to be, and that's for a particular row and a particular column. I would be a column counter, and then J would be a row counter. We're squaring that. So these are just entries in a matrix, and we're dividing that by E for the ith column and the jth row. So we have a counter, or a sum over I. We can say that that's M, and then J goes from 1 to maybe that's L. I'm not sure what I'm using. S and C here. S is the number of, okay, yeah, that makes sense. Makes a lot of sense. So S and then C, because we have multiple samples and then we have multiple categories. So the first sum is over all the samples, the second sum, or the inner sum, is over all the categories, the outer sum is over all of the samples. So first we sum over all categories, and then we sum over all samples. So the way it's going to look, there's going to end up being 14 of these terms in this sum. So the formula looks nasty. It's not too bad. So we'll start with the very, very first. Let's talk about 1, 1. So this is I equals 1, J equals 1. First row, first column. That's literally all I and J mean. They're variables in place for a variable row position and a variable column position. So it's column first, then row in this situation. So for the first column, first row, we have the observed value 12. So this is 12 in parentheses minus the expected value for the same cell or the same entry, 10.78. We square this quantity, and then we divide by the expected, 10.78. That's the first of 14 total ratios. So the next one would be 9 minus 10.22 quantity squared divided by 10.22. That's for the next value to the right of that. If I look at this cell over here, then it's going to be parentheses 12 minus 11.81, parentheses, close parentheses, squared divided by 11.81. And you keep on going until you have 14. And the very, very last one would be here. So parentheses, open parentheses, 6 minus 8.27, close parentheses, squared, then you're dividing that by 8.27. So it's a total of 14 of those. You go all through that table. So all I'm going to do, since I'm lazy, put the first, put the last, with ellipsis, or with an ellipsis in between. So it's going to be, what was it, 9? No, 6. 6 minus 8.27, quantity squared divided by 8.27. So it's 14 total values. So when you're doing this on an AP exam, or on if we were supposed to take a test for this sort of thing, or if this were an AP free response question, which I'm supposed to be giving you guys more AP free response questions, and I will be throughout the week, what we would be doing, we wouldn't have to be writing it this detailed. You could write all of this the way that we were doing it before. So just sum of O minus E squared divided by E. That's good enough. You don't have to make it as detailed as we would normally do in a rigorous mathematics course. So then what I'm going to do, we'll take this and we'll let the calculator find that for us. To do this on your calculator, you could technically go entry by entry, all 14 of them, type all that in, press enter, but it's a lot harder. It's much more work than what we could actually be doing. We'll cut straight to the actual calculator application where we save that data as a matrix, and all we have to save is the observed data. The calculator function already has it built in to find expected counts for us. So you might even get mad at me for maybe suggesting that you had to find the expected counts by hand, which I did find those expected counts by hand. I just edited out the process. But sometimes you're gonna want to know how to do that by hand. By the way, in this situation, you're gonna luck out not knowing how to do that by hand and just relying on the calculator, because usually where they test you how to calculate those expected counts and actually know the procedure, and you wouldn't be able to rely on a calculator to figure out what those values are. It is on the multiple choice part of the exam, which we're not going to have multiple choice section this year. So a multiple choice section, you'd have maybe one or two problems where they would have you find the expected count for a specific cell, assuming that there was no difference between these two populations across that variable or with respect to that variable. So how do I get this done? The way that you get this done is you take just the observed data, not the expected data, just the observed data into a matrix. So I'm trying to remember how to do a matrix again. There's two ways. So the formal way, not the control button, you would press menu. So menu, matrix and vector, this is the main way to get this done. You want to create a matrix number 1. So again, menu number 7 for matrix and vector, create number 1, matrix. And then we're going to tell it how big. So number of rows first, and then number of columns. The number of rows we had was 7 days, and then 2 columns, 2 different samples. So remember, rows are horizontal, columns go vertically. So I'll press OK, and that's what our data looks like, but with no entries in there. So I'm looking to the side on a printed version of the handout what those numbers are. 12, 9, 12, 11, 14, 11, 12, 10, whoops. It was 11, 12, 10, 7, 17, 9, 9, 11, 6. Now before you press enter, we're going to store this as a variable. And the way to get that done, there's a store button, or there's a way to store using the variables button. So above the button for 9, there's the VAR button for variables. That's where they have the store function. So we press control, variable, and we have this little arrow which is going to tell the calculator, store this quantity as whatever it is we're about to write. So then the next thing we got to write is a letter for it, which I'm going to just type in the word or the letter. In this case, just a letter O, because I can get away with just putting in a letter O. Press OK, and every time that I call back that letter O, so if I type in the letter O, press enter, it's going to spit back that information for me. So if you were in an Algebra 2 class or a pre-calculus class, one of the reasons why your teacher might have banned these calculators is that you can do a bunch of quick and easy matrix operations with this. Let's say I want to multiply that matrix O by 2, so 2 times O. And there it doubles all the entries for me. Or let's say I wanted to find the inverse matrix for O. And those of you that you remember your Algebra 2 or your pre-calculus, your inverse matrix, there's a dimension error, and I can't do an inverse matrix for these types of matrices. This is because I completely forgot the mathematics of matrices. Matrices that are square have inverses, or possibly have inverses. So this had to have been a square matrix where the number of columns and number of rows were going to be the same. So no, that was a total fail. But either way, we'll move on. What we were supposed to do, statistics, stat tests, two-way test. So the mathematics are identical, or the statistical procedure. No, that's a lie. The mathematics, so I go back to that. The mathematics is identical for either of these two situations, and the two situations being homogeneity or independent/association. So the math is identical. It's just a matrix, and we're just calculating expected counts and comparing them to observed counts, and it's the same exact formula. What we call them depends on the statistical differences between the situations. So it's a two-way test. So there's only one two-way test, and all they ask for is an observed matrix, and that's it. Assuming conditions apply, there's our chi-square value, there's our p value. Degrees of freedom is calculated to be 6, which I'll explain in a little bit. So these I want to copy down. Calculator gave me 6.549 with 6 degrees of freedom, which I do want to keep track of. Now, how do we calculate degrees of freedom? Which I don't think I gave that to you down here. I probably gave that to you in the next portion of this, where I explain the 4-step procedure for a chi-square test for homogeneity. So the formula for that, how do we get 6 out of, well, it was 7 and 2. There's a way that we do that, and it's a product. So the degrees of freedom comes from the number of samples minus 1. So remember earlier for a chi-square test for goodness of fit, it was number of categories minus 1. So this is going to be number of categories minus 1 also, but it's going to get multiplied by the number of samples minus 1. So for each extra dimension, you take the number of subdivisions for each of those dimensions. In this case, if it's the if we have rows, it's the number of rows minus 1, and then we also have columns. It's the number of columns minus 1, also multiplied with the number of rows minus 1. So number of samples minus 1, number of categories minus 1, and those two get multiplied. So 7 minus 1 times 2 minus 1. 7 minus 1 multiplied with 2 minus 1, which is 6 times 1, is where we're getting that from. So you take each of those two dimensions, number of rows and the number of columns. You subtract 1 for either, and then you multiply those two resulting values after subtracting 1 from it. So here's our formal formula. So here's the formula for a homogeneity statistic. So I wrote it as a single sum. It's really supposed to be written as two sums the way that I wrote it up top underneath the letter C. So it's two counters, I and J, and one stops. One of them is the number of samples, and the other one stops at the number of categories. But in either case, it's a bunch of entries. And in this case, I is just gonna, or not I, S times C is the limiting value. In this case, it was 14. And then there's our formula for expected counts underneath here. So for expected counts, row total times column total divided by the combined sample size, which I called it big total earlier. I'd rather use big total anyway. So the 4-step procedure, same as usual. Step number 1, you state your hypotheses. Step number 2, you name the procedure that's to be used, whether it's an interval or a test procedure. Then you check your conditions, also included in step number 2. Step number 3 is the mathematics. So you apply your formula to find a statistic, degrees of freedom if applicable, and then an appropriate the resulting p-value or probability value. Step number 4, you make a decision regarding the null hypothesis, considering the value or how large the p-value is, and then you make a conclusion, or you state that decision in context and any other conclusions or implications after that. So I'll practice this with number 2, running the full procedure, and then we'll be done with this particular handout. So number 2, the accompanying data on degree of spirituality for a random sample of natural scientists and an independent random sample of social scientists. So comparing two different types of scientists with respect to their degree of spirituality. So let's see, both of them working at research universities appeared in the paper. So the name of the paper is Conflict Between Religion and Science Among Academic Scientists. This is an actual journal article. The Journal for the Scientific Study of Religion, 2009. Is there evidence that the spirituality category proportions are not the same for natural and social scientists, which I'm going to be throwing that back at them and using that for the null hypothesis. Test the relevant hypotheses using a significance level of 0.01, very important. That's the alpha level that we're going to be using. And then we'll go with the null and alternative hypotheses. These will always be done qualitatively. So and I'm going to use their words, like I said earlier. The spirituality proportions are the same, which I might want to insert the word categories in there. So the spirituality category proportions. Because there are different, there are 4 spirituality categories. So in this case, I might need to make some room. Notice how they didn't give the totals for the columns and the rows. So I'm going to be need to be writing those in myself. Spirituality category proportions are, in this case, the same. So are the same for both, and these are 2 different populations that we're comparing for both the first population, natural scientists, and then social scientists for the other population. So natural and social scientists. There's my null hypothesis. Alternative, and then I'll put quotation marks, are not the same for, and then I'll put quotation marks again, period. And those are my hypotheses. Now, before I can probably start the math, I want to set it up so that way I can have expected counts. So I'm going to have to add these together. So the 56 and 56 make up the very spiritual, the first category. So very spiritual, 56 and 56 for both. So 56 and 56, that's 112. They didn't need a calculator for that one. Probably going to want to use a calculator for the other ones so I don't mess them up. 162, 223, 385. Next category, combined 441 people. And then the last category, not spiritual at all, 211 plus 239, 450 total, not spiritual at all. And then what we do, how many natural scientists are there? So then I take the 56, 162, 198, and 211, add those. This gives me the total number of natural scientists. And there's several things I could do. I could just do that again for the social scientists. 56, 223, 243, 239, 761. I can't cheat here. They didn't give me a like a sample size or a combined sample size for either of these. No, they gave me none of that. So they made me work for that all by myself. So then either way, to find the total, big total, combined sample size, you would either add 627, 761, so 627, 761, and I'm getting 1388. Or you could have taken the row totals and added those across. 112, 385, 441, 450. And you would get the same value, 1388. Unless you did something wrong somewhere else. But those two should give you the same. Those two methods should give you the same sum. Next, we name the procedure that we want to use, the inference procedure that we'd like to use, and that would be a chi-square test for homogeneity of populations. If I wanted to be specific, do these 2 populations look the same with regards to this particular variable? So are natural scientists and social scientists homogeneous regarding level of spirituality or degree of spirituality? That's the question. So a test for homogeneity of populations. So you don't have to write the word, or you don't have to write of populations. You could just stop it at homogeneity. So chi-square test for homogeneity is good enough. There are 2 conditions. The beautiful thing about chi-square testing, the conditions are the same for all 3 of them. So there are 2 conditions. First one, random sample, or we have the results of a randomized experiment. So we'll get to that later. We might see that in the next handout. So randomness, some way, somehow. So a random sampling procedure or randomized treatment assignment, some way, somehow. And then the second condition, expected counts are very large, and large enough would be 5 all the way across. So we have 5 expected for every entry. So really all we have to do is figure out what those expected counts are. And since we have a calculator, I'm not going to do those by hand. You can maybe show the work for one of them by hand, but I don't know why you would. So what I'm going to do is I'm going to give an expected table. So expected counts table. And it's supposed to be what, 4 by 2 or 2 by 4? 2 rows, 4 columns. So it's 1, 2, 3, and then 4. So what I'm doing is I'm going to do this on another table separate from the one that's already given up there. Just because I guess I feel like doing it on the table, filling up all the space that I have here. So what we'll be doing is giving the expected counts that result from the calculator. So we'll be going to a calculator then. So how to get this done in a calculator? We will want to do the same thing that we did earlier. Oh, the problem is what I haven't shown you guys how to do is extract the expected matrix. So these are the results from the previous problem. So that was the previous problem that had 7 days of the week and then 2 samples. There's an expected matrix there that we're going to want to extract. Now, not for this problem. However, I could have shown that one just to show it against the work that we did by hand. But we'll just go straight to the other problem. So the other problem, or number 2 that is, we're going to want to save another matrix. So menu, matrix and vector create, and then a matrix, and this time it's a 2 by 4. So 2 by 4, yeah, and it starts with 56, 162, 198, 211, 56, 223, 243, 239. And then this one, we could just save it under the same name. It'll write over it. So store as and then O for observed. And then run that test all over again. So what I'm going to do is I'm going to copy paste that. Actually, no, that's a bad idea. I should show. So statistics, stat tests number 7. And then we want two-way test number 8. Observed matrix is O. Press OK. There's our chi-square value, our p-value, degrees of freedom, but what I really wanted right now is the expected matrix. So how to extract that? So every time you run a test like this, the program or the coding behind that function includes the storing of variables most of the time. So a lot of the times we can find out what those variables are, and they should still be stored in our calculator, and this one is. So expected matrix is exp matrix, so stat.exp matrix. So how did I come up with that list? I pressed the variables button. So the number above the number, or the button above the number 9. So VAR for variables. So these are all the variables stored in our calculator at the moment. And the ones with stat dot something, those are all the ones that were created by the statistical application that we use, in this case the two-way test. So we want stat.exp matrix. Press enter twice, and those are all of the expected counts. You don't have to do them by hand whatsoever. The work that you have to do is type in the observed matrix first. So the observed matrix stored as a variable. Input that into your test function. It spits out the information for the results of the test. You can extract using the variables button the expected matrix, and here they are. So it's really, really quick and easy. So what I'm going to go ahead and do is I'm going to go ahead and copy those down onto the handout. So here are the expected counts. I went ahead and just wrote them in. And what we're going to do is we're going to use that for the second condition. So I have 2 bullets here on the side. So the first bullet is we have a random sample. So random sample is given. Actually, no, random samples, because there's 2 random samples. And I need to be a bit more specific here. So because there are 2, these need to be independent random samples. So 2 independent random samples. Check mark. Second condition, all expected counts in the table shown to the right. Point to it are greater. They should at least be 5. So if one of them is a 5, or if there's multiple ones that are 5s, that's okay too. Check mark. But here I'm making a stronger argument. They're all bigger than 5. And there's our second step. So the first step was to give the hypotheses, HO and HA. Then the second step was the naming of the procedure and then checking the conditions for using that procedure. Step number 3 is the mathematics. Very first step in the mathematical portion, chi-square equals, and you could write a sum, O minus E squared divided by E is going to equal to, and again, there's going to be, well, in this case, there's not 14. In this case, it's 2 by 4, so that's 8. 8's still too many, in my opinion, so I'm going to do the first. So 56 minus the corresponding expected value, 50.59. Square this difference, you divide by the one that's expected, 50.59. Plus, dot, dot, dot. Maybe we want to move this a little bit further down. And we do the last one, 239. Minus the corresponding expected value, 246.72. These two, the difference is squared. You divide by the expected, 246.72. And that comes out to be, according to the calculator, like we saw earlier, 3.091-ish degrees of freedom, which I could show the work. 2 minus 1 times 4 minus 1, that ends up being 3. 1 times 3. P-value, calculator gave us 0.378, which was not a statistically significant result. That's a high value. So since, I'm going to go ahead and put, first off, this is greater than alpha, which is 0.01, and I'm not going to say that again. I'm going to say since the p-value is large, and it should be obvious to whoever's reading this what I mean by large. P-value is large because it's greater than alpha. We fail to reject. We reject when it's low. So in this case, smaller than 0.01. Fail to reject. The null hypothesis, which I've already stated what that null hypothesis is, and I've given a symbol to it, HO. Then we're going to go ahead and just restate it anyway. There is enough evidence. No, sorry. Unpause. 3, 2, 1. So what's the conclusion? There is not enough evidence, or there isn't enough evidence. To conclude, and what was this? These were natural scientists and social scientists. That natural scientists and social scientists, not enough to write that. So conclude that natural and social scientists differ in their degree of spirituality. So what does that mean? It means the test didn't really detect a difference between the expected counts and the observed counts here. So those observed counts weren't very far off from what they should have been. And they don't really look too far off. So that's going to be it for this particular handout. We'll come back for the next one, 10.5, which goes over tests for association or independence of variables.